Hey everybody, Chapter 1, Lesson F, Part 2. We're going to solve equations algebraically now using square root, absolute value, and rational functions. We're also going to talk about something that shows up once we're outside the realm of just polynomials like linear, quadratic, cubic, etc. Once we start analyzing and finding solutions and solving equations using the following functions, it's possible that the solutions we find might not actually satisfy the equation. This is called an extraneous solution. Okay, so an extraneous solution we're going to talk more about in this lesson, which is a solution that doesn't actually satisfy the equation that it was given. So it's like a false solution that we need to be aware of. So what we'll do is we'll go back and we'll test each of the solutions in the scenarios that we're going to see today. So let's go ahead and get started. Okay, so here we're going to define solving again to solve an equation means to find the x values or independent variable for which the equation is true. This is very important that we go back and we check our solutions today such that we can find whether or not the solutions we found were actual solutions or called extraneous solutions. So let's go ahead and jump in and algebraically solve this first, and then we'll look at it graphically. So anytime that you have a square root, in order to isolate x, what we want to do is we want to square both sides. And when we square a square root, those inverse operations negate each other, leaving us with x minus 4. And when we square 3, we get 9. Therefore, we would see that x equals 13 should be a solution to this equation. Let's see if that's true. So let's plug in 13 minus 4, which equals the square root of 9, which equals 3. Therefore, we could say confidently that x equals 13 would be a solution to this equation. If we graphed this, let's take the equation square root of x minus 4. Let's say that this is the parent function square root of x shifted to the right 4 units. And we want to know where it equals 3. So if we were to go up 3 units, we would see at this point, and this is not to scale clearly, at x equals 13, that we would have the intersection of those two equations. Okay, so clearly, visually, and we're going to do a lesson on this using the graphing calculator, there is a point of intersection there. It makes sense that there'd be only one solution, seeing that the square root function would continue to increase in its output values, whereas this line, y equals 3, would continue on forever in a constant rate. Okay, so let's look at a few examples on the next slide. Okay, so I'm going to go into solving algebraically for each of these different types of functions. And then after we find our values or our solutions, we have to go back and check them in the original equation. Let's start with number 1. For number 1, the first thing that I would do is I would square both sides. And I would square both sides after I brought the x over to the right side. So first add x over, then square both sides. Looks like I would get 2x plus 7, and then I would have to FOIL this. I'd get x squared plus 4x plus 4. Getting everything to the right side, I would have x squared plus 2x minus 3. And I believe that will be factorable. It will be factorable as two linear factors, x plus 3 and x minus 1. Those 2, 3, and negative 1 would multiply to negative 3 and add the 2. Therefore, x equals negative 3 and x equals 1 should be solutions. Let's check and make sure that's true. So let's take the original equation and confirm that the following is true. So let's plug in a negative 3. Okay, so if I plug that in, I would get a square root of 1 minus a negative 3, which would be plus 3. That comes out to equal 4. That is not equal to 2. Therefore, x equals -3 is not a solution. Let's do the same process now using a 1. Okay, so that would be square root of 9 minus 1, which is 3 minus 1, which is equal to 2. It looks like we do get what we wanted. Therefore, x equals 1 is our only solution in that particular scenario. Okay, let's look at number 2. If I were to divide both sides by 2, and by definition of an absolute value, what this does is it splits off into two situations. Okay, so if the absolute value of x equals 1, that means that x equals 1 and negative x equals 1. Therefore, I could say x minus 5 equals -2, and the opposite of x minus 5 equals -2. So that would mean x would have to equal 3, as well as negative x plus 5 equals -2. Therefore, x would equal 7. Let's check and make sure that those are solutions. Potentially, it won't be. And I don't believe either of these are solutions. So if I plug in a 3, that would be 2 times the absolute value of -2. Well, that comes out to be 4. That's not equal to -4. So 3 is not a solution. If I were to plug in 7, I would get 2 times absolute value of 2, which also equals 4, which is not equal to -4. Therefore, this equation has no real solutions. Okay, and it makes sense. If you were to graph, let's look at this step right here. If you were to graph the absolute value of x minus 5, that's the absolute value of x shifted right 5 units. That's what that graph would look like if that was a 5. And does it ever equal -4? The answer to that is no. Therefore, there would be no solutions. Okay, let's look at a rational function. Okay, so we have to be aware initially that we don't get x equals 0, because that would cause an issue here. That'd be outside the domain. And we don't get x equals 2. So if we get a value equal to either of those two, we know it will be an extraneous solution. But let's work through the rest of it. So 2 over x equal to 3 over x minus 2 plus 1. Wouldn't it be nice if we didn't have to work with fractions? Well, we can do that. What we do is we clear the fractions by multiplying by the denominators that I see throughout the problem. So as I distribute x times x minus 2 to both sides of the equation, watch what happens. When I distribute on the right side, the x's cancel, and I get 2 times x minus 2. On the right side, I'm going to distribute to both of these terms individually. The x minus 2's will cancel in the first one, leaving me with 3x. And nothing will cancel in the second, leaving me with x times x minus 2. Now, I do recall that I had made a mistake when I was transferring this problem over. I wanted this to be minus 1, which would just change this sign to a negative, which would just change this sign to a negative as well. So let's continue and see what we get for our x values. So that gives me 2x minus 4 and a 3x and a negative x squared plus a 2x. Okay, so if I bring everything over the left, and I would bring everything over to the left side of the equation because I want the leading coefficient to be positive. So I'd have x squared. It looks like I would have a negative 3x and a negative 4. Okay, it looks like this is factorable. I like what I see. So what I would do is factor two numbers that multiply to -4 and add to -3 would be -4 and a +1. So x would equal a -1 or x could equal a +4. So let's go back and check just to make sure. Clearly there's no issue with the domains that we talked about. So we don't have an issue with x equaling 0 or 2. let's check and see what happens when we put in a -1 and when we put in a +4. So let's test -1 first. Okay, we plug in. On the left side, I'd get -2, which would be -2. On the right side, I would get 3 over -3 minus 1, okay, which would be equal to, that'd be -1 minus 1, which is -2. Since those two are equal, then x equals -1 would be a solution. Okay, so it satisfies the equation. If we test that with 4, okay, I would have 2 over 4, which is equal to 1/2. On the other side, I would have 3 over 4 minus 2, which is 2, minus 1. 3/2 minus 1 is also 1/2. Since 1/2 is equal to 1/2, 4 would also be a solution. It looks like both solutions are actual solutions, neither are extraneous. Okay, this fourth type you'll see on occasion, but I would like to rewrite it, and it might make more sense to you. But x plus 1 to the 2/3 power, notice that that's fractional or rational, would be the same as x plus 1 squared to the 1/3 power is equal to 4. Now, I would like to undo that 1/3 power by cubing both sides. If I cube both sides, I'd be left with x plus 1 quantity squared is equal to 4 cubed, which is 64. I'm going to take the square root of both sides, and in doing so, I will get x plus 1 is equal to plus or minus 8. Therefore, x is either equal to 8 minus 1 or -8 minus 1. So I would get 7 or -9. All right, so we'd go back in, we'd test, and we would find, I believe, that both of those, let's see, yeah, both of those would end up being solutions. You could check that on your own, but both should be solutions. Let's move on to a few more questions like this, paying close attention to extraneous solutions. So as you might have noticed, after working with square roots, absolute values, and rational functions, what you'll end up doing is getting them into a form that's quadratic or cubic or linear in nature. Therefore, it does all boil back down to the methods we use to solve polynomial equations, which were factoring, extracting roots, quadratic formula, possibly factor by grouping, but it comes down to eventually using those basic skills that we learned in the last lesson. So let's go ahead and get a couple more repetitions in on doing these problems, and then we'll get you some time to work on some practice. Okay, here I've got another couple of examples where extraneous solutions may appear. So the definition of extraneous solutions is given above. You can go ahead and read that on your own time. I'm going to jump right into the problems and find the solutions to the equation, being aware of the extraneous solutions that are possibly present. So let's get into the first one. Let's clear fractions. Okay. Notice that x squared minus 4, this expression here is actually x minus 2, x plus 2. So I'm going to multiply both sides by x plus 2, x minus 2. All right, so on the left side, what we'll notice is that the x minus 2's will reduce. So I will get x plus 2 times 1. Okay, on the right side, maybe I'll move that down just a tad. So I'll get x plus 2 times 1. On the right side, with the first term, the x plus 2's will cancel, so I'll get 3 times x minus 2. In the second term, x squared minus 4 will reduce with the entire expression x plus 2, x minus 2. Therefore, I will just get minus 6x. Now this is linear. This is great. It's a nice, easy function to solve and find solutions for. This would be 3x minus 6 if I distribute, minus 6x. So it looks like I will get, on the left side, 4x On the right side, I will get a negative 8. Therefore, x would equal negative 2. Okay, so if that's the only possible solution, we're going to have issues because check out what happens here. It's going to be a problem because I see that x plus 2 is in the denominator of at least one portion of this equation, which means that I'll have an undefined value, right? So at the very beginning, I should have wrote out that we know that x cannot equal 2 or negative 2. And now we would see that that restriction comes into play. Therefore, there would be no solutions for this equation. Okay, let's move on to the second part. Okay, again, I see a square root. I'm going to go ahead and square both sides. You always want to get that square root alone. We'll see that come up in a problem coming up here soon. So I would get negative 2x plus 30 is equal to x squared. I'm just foiling this out, minus 6x plus 9. Let's bring everything over to the right, so I have a positive leading coefficient. That would be negative 4x and a minus 21 if I brought that 30 over. That looks factorable to me. Factoring is always favorable over most of the other methods, provided that it's leading coefficient of 1. Sometimes there are other more advantageous methods, but in this case I would have x minus 7 and an x plus a 3. So that would tell me that x equals negative 3 and x equals positive 7 are potential solutions, but I need to test them. Okay, so I'm going to test the left side with negative 3. That would give me negative 2 times negative 3 is 6 plus, so 6 plus 30 is the square root of 36, which will equal 6. On the right side, if I plugged in negative 3, I get negative 3 minus 3, which equals negative 6. Those two are not equal. Therefore, negative 3 is not a solution. Okay, I'm going to test with, let's test with 7. So that would be negative 14 plus 30, which is the square root of 16, which will equal 4. On the right side, I would have 7 minus 3, which is 4. Since 4 equals 4, x equals 7 would be a solution. Therefore, x equals negative 3 is an extraneous solution that you need to be careful for. Okay, let's go on to another couple of problems here on the next slide, and then I think that'll be it for the day. Okay, a number of different ways we could do the first one here. I see two radicals involved. I don't really want to square while both radicals are on the same side, so I'm just going to move one of them. So I'm going to rewrite this as square root of 2x plus 6 is equal to 1 plus the square root of x plus 4. Okay, now when I'm working with radicals like we've done before, at least square roots, I'm going to square both sides and see what we have left. So I'd have 2x plus 6. On the right side, I'm going to FOIL this out. You can FOIL it out on your own, but what we would get is 1 plus 2 square root of x plus 4s plus x plus 4. Okay, if you got questions about that, please let me know. Okay, now I do have a radical left. What I'm going to do is move everything other than this term, 2 times the square root of x plus 4. I'm going to move everything else to the left side. So if I subtract x and I subtract 5, I get x plus 1 is equal to 2 square root of x plus 4. Now again, I'm going to square both sides to get rid of that square root. So on the left, I get x squared plus 2x plus 1. On the right side, that 2 turns into a 4, and the square root of x plus 4 turns into just x plus 4. Now I hope I can factor using the methods that we had before. Okay, let's see what we got. I might need to use the quadratic formula. We'll see. Maybe not. So I'm going to subtract 4x, makes that negative 2x. And then subtract 16 makes that negative 15. Nice, I don't have to use the quadratic formula. I'm going to be able to successfully factor this. Two numbers that multiply to negative 15 add to negative 2 are negative 5 and a positive 3. So x should equal either negative 3 or x should equal 5. Okay, so if we were to go back and check whether x equals negative 3 and x equals 5 were extraneous solutions, we could determine whether or not it would satisfy the following. So let's go ahead and do that. I'm going to plug in a -3, and I'm going to do this in somewhat of a simpler way. You need to do this as well and show valid reasoning algebraically in the process. So what I would get if I plugged in a -3 would be the following. Okay, if I plugged a -3 into the first, I would get square root of 0. If I plug in -3 into the second, I would get square root of 1. Well, that's 0 minus 1, which is -1. Therefore, x equals -3 would not be a solution for this equation because it does not come out to be equal to +1. Okay, if I plug in a 5, okay, if I plug in that 5, the first radical will be a square root of 16. The second radical will be a square root of 9. So the square root of 16 minus the square root of 9 is 4 minus 3, which comes out to equal 1. Therefore, x equals 5 would be a solution to that equation. Okay, let's look at our last example of the day. Remember that the absolute value, by definition, if absolute value of x equaled 5, then that means that both x would equal 5 and negative x would equal 5. Therefore, in this case, if I've got absolute value, this is a very unique situation, I would have that x squared minus 3x equals -4x plus 6, or the opposite of x squared minus 3x is equal to -4x plus 6. So let's algebraically get everything on one side. I'm going to have x squared plus x minus 6 equals 0. And over here, I would have the opposite of x squared plus 3x equals -4x plus 6. If I brought that the terms on the left over to the right, I would have x squared minus 7x plus 6. So I can factor both of these equations. I would have x, I would have plus 3, I would have x minus 2. I've got a little person talking to me. Hold on, buddy. Okay, and then the other one, I would have x minus 6 and x minus 1. Okay, so that's telling me then that I should have solutions of -3, +2, +1, and a +6. Now in this process, we would go back in and we would check all 4 of these, okay? I believe, based on this, that we would have 2 real solutions, 2 actual solutions, and 2 extraneous solutions. So if you come back after working through that, I will expose which ones were extraneous and which were not. So based on calculations, the 2 extraneous solutions were 2 and 6. Our actual solutions are -3 and a +1. Okay, guys, that is solving equations involving radicals, specifically square root, absolute values, and rational functions, being aware of the extraneous solutions. We'll see you next time. Can you say bye, buddy? Say bye?
No.
Oh, okay. He doesn't want to say bye. Have a nice day. See you next time.